Yesterday, we reminded ourselves of how we model a continuous sum with a discrete sum. We did this framing it as trying to find area equals length times width when the length is continuously variable. Continuously variable is a problem for multiplication because multiplication says all the terms need to be the same. When all the terms aren't the same, we use addition. And when our function is continuously variable, we assume that the function is constant. Our continuously variable is constant for some small change in x. So that's what's going on over here in the Riemann sum. So here we assume f of x is constant for some small changes in x. Once we make f of x constant for small changes in x, we can calculate area is equal to length times width. And since we're doing this for small changes in x a bunch of times, we can add up the values. The weird thing happens when we go from our discrete sum with an infinite number of rectangles to our continuous sum. The thinking should still be the same, even though mechanically it's not going to work out for us. The thinking should be the same. I'm going to take this expression f of x dx and evaluate it for all the relevant values of x. Evaluate the expression f of x dx from a to b for everything on the interval from a to b. So the integral is telling us what to plug into the expression. The integral is telling us what to plug into the expression. The integral from a to b part is telling us what to plug in. That's the part of the description that we want to grab onto, because we're upgrading this problem today. We know that this can be used to find the area under a curve and above an interval, the interval that we're trying to plug in. So this is going to give us the area under the curve and above the interval. We're finding the area, which is length times width. Under the curve, which is the function. And above the interval, which is our subset from a to b. We know we want to upgrade this problem to deal with the function of two variables. We're going to upgrade this problem to deal with a function of two variables. When we replace our function of one variable with a with a function of two variables, we are looking at a surface So a function of two variables will give us a surface and now instead of just plugging in a bunch of x's, we need to plug in a bunch of x's and y's. So we're going to plug in a bunch of x and y. So we're plugging in from some region in the xy plane. In the previous problem, we had the space between a one-dimensional curve and a one-dimensional interval to get a two-dimensional area. Here, we're finding a volume between areas. So we're finding a volume.
This is a security advisory. Please maintain possession of your bags at all times. Please report any suspicious activity or unattended items by calling 9.
Have a nice flight. So instead of the area, which is a two-dimensional area, the space between two one-dimensional things, we have between a surface and a region, we have a volume between two areas. And we're going to calculate volume as height times area. Normally we would write area times height, but we're going to be thinking about it as height times area because the height is going to be the function, just like the length was the function, and our width in the area was our delta variable. Our area is going to be the delta variable. Question? Let's draw a quick picture. This will look very much like what we had yesterday. The problem that we're going to run into is describing this bunch of x and y. We're going to have the tricky thing that we have to deal with now is that we have to describe what values of x and y we're plugging into our volume expression. This is going to be the tricky part. It's not really the tricky part. It's just the new part. So the new thing that we have to deal with now is describing the values of x and y that we want to plug into the expression, because that's all we're doing with this integral. Thinking of the integral in these terms. The integral from a to b, that's just the set of x that we're plugging in to f of x times dx. We got away with this being really easy before because we're looking at a subset of the real number line, a one-dimensional thing. All we get is an interval. The only way to grab a bunch of x's to plug into our expression f of x dx is to grab an interval. But with a region can have some kind of shape to it. And so now this is the new difficult part of our job, describing that shape. Describing all the x and y to plug into the interval. Or sorry, into the expression for volume. Describing an interval, a subset of a one-dimensional real number line. Very simple. Start here, end here. Describing a region is more complicated because regions can have different shapes. So this is tricky because regions can have different shapes. Maybe we're plugging in over a rectangle. Maybe we're plugging in over a circle. Maybe we're plugging in over like a piece of a parabola. Maybe the floor is a parabola. Or maybe someone's just really being a dick. We have to find a way to describe all these values of x and y to plug in. Very simple with the function of one variable. Here's a bunch of x's. That's it. Here's a bunch of x, y that has shape to it. We have to figure out how to describe that shape in a way that the expression will understand. Any questions? All right. So let's draw a picture of how our thinking goes. Let's apply this thinking. We're going to do the same thing that we did before. We're going to have a function of two variables. We're going to assume that that function is constant for some small change, not in just x this time, but also some small change in y. So we're going to have this little rectangle down on the floor with a delta x times a delta y, and then we'll evaluate the height at some point in that little rectangle. So what it will look like So remember what we're going to be thinking about. We're thinking about some function of two variables, which is going to be some surface. We're going to look at a little piece of that surface. We're going to apply the same thinking. We're going to assume for some small change in x and some small change in y, that the function is constant, that the surface is flat. So for some small change in x, and some small change in y, for some small change in x and some small change in y. For this little patch of floor, we're just going to make the function constant. And we're just going to take some point from that little patch and evaluate the function. So we're going to pick a point in that little rectangular patch and use the height of the function at that point as the height, as the value of the function all over that patch. We're going to flatten the function out on that little patch. Going to name the point. Now, before we just had x's. So we could call them x1, x2, x3, x4. Here we're going to have x1, x2, x3, x4, but we're also going to have y1, y2, y3, and y4. So we're going to have indexing on the x direction and indexing in the y direction. So here I'll pick this point, I'll call that xi. And here I'll call the point yj. I have different indexing. Now we're going to calculate the volume of this rectangular solid in the normal way. take that little area, and we'll call that delta. I'm out of colors. The colors just got all messed up. There's some small change in area, which is just length times width, delta x times delta y. And now I'm just going to calculate the volume of that rectangular solid. So we're going to have the height given by the function, evaluated at xi and yj. That's the height, and we're going to multiply that by the area. And there's the height of one of the rectangular solids. I have my representative height for the function over that whole small piece of area, that's whole small delta A. And I'm calculating volume the same way we always calculate volume. Cross-sectional area multiplied by the height. We could also think of delta A as an area delta x by delta y. So we can also think of this as f at xi, yj. As the air as delta, we can think of delta A as delta x times delta y. We're calculating volume the same way we always calculate volume. Length times width times height. Or in this case, height times length times width. The names don't matter. Then we construct our Riemann sum. Now our Riemann sum is a summary. We use this sigma notation. It says add this fxi times delta x for all these values of I, as I runs from 1 to n. So we're going to have to do two sums, because I've got I running from 1 to n and j running from 1 to maybe even something else. There's nothing that says we have to slice this up in the same way. But then we add up all the rectangular solids. We're just evaluating f at xi, yj, delta x, delta y, and I'm going to add up. X went first, so I'm going to say as I goes from 1 to n, because I've divided my region up. I goes from 1 to n, and I also have to add up as j goes from 1 to m, because we might have a different number. I listed the I indexing first because I listed delta x kind of closest here. I listed j second on the outside. Note that the thinking was the same. I'm chopping up my region, whatever my region might look like, I'm chopping it up so that I've got a bunch of delta x's and a bunch of delta y's. I'm just looking at it as a bunch of squares, and for each of those are rectangles. And for each of those rectangles, I evaluate the function at some point in that rectangle. And I use that. I'm thinking that the function is constant over that, on top of that small rectangle, the same way we did with the original, with our single variable integral. The next step was to turn this into a definite integral, wherein we describe the value, the set of x that we plug in to this expression. And our function, f of xi yj times delta x delta y, or our expression, f of xi yj delta x delta y, is going to become f of xy, our continuous function, times dx and dy. So this is going to become our double integral over some region. I'm going to use R for region of some of our continuous function f at xy for the height times dA and our dA is going to be made up with a dx and a dy. We're not doing anything new in our thinking. Our new task is to just figure out how to describe the set of x and y we want to plug in. That's our new task, how to describe that set. The reason that this is our new weird task is that a set of xy can have a bunch of different shapes. A set of x, it's going to be an interval. But a set of x and y could be some funky shape. Could be very simple, very simple, very simple, or kind of messed up. Any questions? So to this end, we're going to be less concerned about what's going on with the function and more concerned with what's going on down here on the xy plane. Our task is to describe the region with some x values and some y values. How are we going to describe the region? So we're going to look at this from the top down. So that R is some region in the xy plane. Now remember, in our single variable version, we just had to say an interval. We just had to declare an interval on the x-axis. We're just saying what's x between. X is between A and B. What's x between? So it's very sophisticated describing the region R in a double integral, because we're going to do what's x between and what's y between. That's all we're going to do. We're going to be saying what's x between and what's y between. Or the other way around, what's y between and what's x between. Or the other way around, what's y between and what's x between. The new thing, whereas in our single variable integral, what's x between was just going to be two constants. Now what's x between and what's y between, one of them will be constants and the other one will be variables. So let's take a top-down view. There's going to be some surface. We're looking through the top of the surface, and we just want to divide up a region. And let's say that the region is a rectangle. Let's suppose I've got this rectangle where the y values go from 0 to 4 and the x values go from 1 to 3. And there's my region R. This is the best one to start with because this is the most direct extension. This is a rectangle is just two intervals. X from 1 to 3, that's an interval. Y from 0 to 4, that's an interval. A rectangle is just two intervals. So we got to tell our what to plug into the expression fxy times dA. Now the dA can come in two varieties. We can write dA as dx dy or dy dx. So in this case, the order that we write dx dy matters as far as how we set up the double integral, because the integral goes with a particular dx or a dy. So in the integral dx dy, this first integral closest to the function, that's our x integral. So that's where we're going to describe what x is between. And then since dy is outside, that's our last integral. That's where we're going to describe what y is between. In our dy dx integral, dy is closest to the function, so the integral closest to the function is our y integral. What's y between? And our dx integral is outside or last, and so that's going to be what's x between. We got to be all organized, how we set things up. In the case of a rectangle is just two intervals. We just have to say what's x between. X is from 1 to 3. And what's y between? Y is everything between 0 and 4. In the dy dx integral, everything is the same. Y is from 0 to 4. And x is from 1 to 3. We think about doing the integrals from inside out. So when I describe a double integral, I'm going to refer to this inside one as our first integral. And then the outside one, sometimes I'll say outside, but I'll also say the last integral. So when I write dx dy, dx is our first integral, dy is our last integral. I know it's weird to call one first, and when there's only two of them, call the second one last, but eventually there's going to be more than two, so that's why. I read the manual for a car I had, and it was a two-door car. And they say, press the button on the key fob to unlock all the doors. And it was weird because there's only two doors. When there's only two, when you want, instead of saying all, we'll typically say both, right? Think about how weird that is. Like, open all the doors in this room. There's only two doors in the room. If I said all the doors, you'd like look at the cabinets over. It's like the cabinets too. I'm like, oh no, just all the doors. Like, oh, but those are doors. But if I said both doors, it would be super clear, just those doors. You know what I mean? So it's weird when I'm like, oh, first integral, last integral, when there's only two of them, instead of just saying second integral. But eventually there's going to be three of them. And so it's going to be a first, a second, and a last. So I'm just going to start calling this one the last integral now. So we're just trying to describe this region. I need a little more room to work, so I'm gonna go from 0 to 3 on the X and from 0 to 9 on the Y. But here's what our region is going to be. I want to describe the region. I'm gonna draw a line. Let's just go from this corner, 0, 0, up to the corner 3, 9. So let's say that the region that we're describing now, we're going to evaluate the function on over this triangle. And we're going to describe this with two double integrals. Because remember, we can say what's x between, what's y between, or we can say what's y between, what's x between. It didn't matter in the previous example because we had a rectangle, just two intervals. But here, even though x goes between 0 and 3, y starts off at 0 but ends at this line for different values of x. So for each value of x, y ends in a different place. So note that for each value of x, for each x, y ends at a different place. For each value of x, y ends at a different value. Also note that for each y, x ends at a different value. Or I should say x starts at a different value and ends at 3. Y always starts at 0, but ends at this line. X starts at the line, but ends at 3. For each y, x starts at a different value. So for an x, for a particular x value, I'm going to say that y goes from 0 to the line. But x is different. For a particular y value, x starts at the line and ends at 3. What's x between? What's y between? There's one more rule that we need to have before we can write this double integral. The last integral has to be between constants. No variables in the last integral. Last integral, interval only. Whether it's x or y, the last integral can be an interval only. So if in this double integral, dx dy, dy is the last integral, so I can only put an interval for my y's. And I just look at the values of y that we're between, where y goes from 0 to 9. The last integral is interval only constants. That means to describe this triangular bit, this is where I'm going to have the line show up. X will go from the line and stop at 3. In the other order, dy dx, where dx is the last integral, or sorry, dy is the last integral. Oh, now the colors are confusing me. If my last integral is the dx integral, then I have to use constants for this last integral. So I can only say for x goes from 0 to 3. Then for each x, I look at what y is between. Y starts off at 0 and ends at the line. So we're saying what's x between and what's y between. We're going to try, we have to try to describe, we're trying to describe things like a rectangle. And there's 2 orders we can do this, dx dy or dy dx. The last integral can only use constants. It has to be an interval. So any curve or variation that we have, that's taken care of with that first integral. That's where any variable parts need to show up. All right. Remember, the thinking is no different. What we're doing is trying to describe the region over which we're integrating. We're just trying to describe the region, that set of x and y. That's what we're trying to do. Describe the set x, y that we're plugging in to our volume. That's it for today. I will see you all on tomorrow. Everybody have a good day. And thanks for playing.